got a load of stuff to cover. Okay, so hi all. Okay, so last time we were talking about measurements. In particular, we talked about how, at least if you don't look at the outcome of a measurement, then you can sort of understand all the effects of it just by thinking of it as unitary evolution that entangles your system with your measurement device. This is called decoherence. Of course, when you actually look at it, then you do still need more to explain what's going on, because you need to explain why you only see a single measurement outcome, and that's where the measurement postulate comes in. And then we also talked at the end a bit about sort of generalization of the notion of doing a measurement called a POVM, which basically means you have some arbitrary unitary interaction between your system and your measurement device, and then the measurement device gets measured in the computational basis, and on big basis. This is sort of the most general formalism that can describe a measurement. Okay, so today we're going to move on and talk about a couple of things. So they're both going to be slightly brief. We've got quite a bit of content to cover. First is going to be about distinguishing different density matrices. Okay, so if you have two pure states, then the natural measure of how similar they are is their inner product. But for density matrices, it's a bit more complicated, and there's a couple of natural measures you might want to use. I'm going to briefly introduce both of those, just because they're things, if you do more quantum information, you're going to see all the time. And the second thing we're going to talk about is what are the sort of natural maps between density matrices, ways density matrices can sort of evolve into other density matrices. And these are something called quantum channels. Okay. So I should say, just if you want to do extra background reading beyond stuff talked about in the lectures or the notes, this sort of topic of the course, this sort of more information-y section, is not really done in any detail at all, or really done properly in Riefel and Pollock. So if you do want to read more details about it, then I recommend Nielsen Zhuang, which is sort of this classic Bible of the subject, and it's called section 3 of that is all about this sort of more real quantum information as opposed to quantum computation sort of stuff. Okay, it's a bit more technical than we're going to be in lectures, a bit more precise, goes in more details. It's really a reference book rather than a introductory book, but it will contain any details you want to know. Okay, so let's start in the real content. So as I say, if you have two pure states, ket psi and ket phi, then the sort of, the thing that controls the distance between them or determines sort of how similar they are, how distinguishable they are, then the distance between them is characterized by the inner product. And in fact, really, because the phase of these states is not physical, then it's really the modulus squared of the inner product, right? That's the thing that's independent of global phase of each of them. In particular, if this inner product is equal to 1, if they're normalized, I'll assume they're normalized, means that they're the same state. And if it's equal to 0, then it means they're orthogonal, means they're maximally distinguishable. Okay. So the aim of the first part of this lecture is just going to be about how we generalize this formalism to density matrices, what the right more general definition is for a density matrix. And there's going to be two definitions that we're going to see. They're distinct things, but they're sort of similar, and we'll see that they're related in a certain way. First is going to be called the trace distance. And the second is going to be called the fidelity. Okay. So the trace distance is defined what's called operationally. It's defined by how well you're able to do some physical thing. And it's defined as follows: how confidently can you distinguish rho and sigma, are two density matrices, by a single measurement. Okay, so we want to do some measurement that has some projector that we can maybe call P rho, that corresponds to a conclusion that the state is rho. And then we obviously have P sigma. It's the opposite conclusion, so it's equal to the identity minus P rho. And we want to choose this to maximize the probability that we correctly conclude that it's rho minus the probability that we incorrectly conclude that sigma is actually rho. Right, so we want to maximize trace of P rho times rho minus, that's the probability of measuring that it's rho if it's actually rho, minus trace of this P rho given that it's actually sigma. Okay, makes sense. So just to write that as a simple formula without so much overhead, we define the distance, trace distance between rho and sigma, just the maximum over all projectors P of trace of P rho minus sigma. You might ask, wait, what about these more generalized measurements involving positive operators? Pi, shouldn't we define it that way, right? If we're wanting to work out how we can best distinguish the two. It turns out you can replace the projector P by some positive operator pi greater than 0 without changing the definition at all. Like the maximization P projector is a positive operator, and it turns out that this formula will always be maximized by a projector just because, sorry, this should be, identity has to be bigger than pi so that it can, pi plus 1 minus P also has to be positive. And yeah, it turns out that the maximization would always be maximized by a projector anyway. Okay. So that's just an aside. But yeah, this is a physical definition. It's just maximizing this probability difference between the probability measure this outcome if you get rho, if you had rho, and if you had sigma. But we can be a bit more explicit than that, just by writing rho minus sigma in its eigenbasis. Okay, so rho minus sigma is just a matrix, so it has an eigenbasis. Note, of course, that in general, rho and sigma will not commute, so they will have different eigenbases. So it's not equal to the eigenbasis of rho or sigma themselves. But it's a matrix, it has an eigenbasis, so we can write it as rho minus sigma equals sum over I, lambda I, psi I, psi I. Okay. And
Sorry,
we want to, yep.
What is NB?
Oh, so that just means node.
Oh,
Sorry, that's just that's nothing to do with physics. Let me change it to saying note so it doesn't confuse anyone.
and just one more question. Are the Krauss operators, are they unitary or Hermitian or neither?
Neither. Yeah. That's a good question. They're going to show up again today, but they surprisingly general. But the only constraint on them you have is this sum over ki dagger ki equaling the identity. That does put constraints on the individual ki's, right? Because each ki dagger ki is a positive operator, and so if one of them is already each of them individually has to be smaller than the identity, so they can add up to the identity.
So do like the projection operators, are they like part of the set of this like bigger group of these pi operators?
Yeah, so projection operators, yeah, projection operators are positive operators, so that they're an example of a PVM is an example of a POVM. It's just generalizing the formula to allow a larger class of operators associated to each measurement outcome.
All right, thank you.
Okay. Cool.
How do we know that the eigenbasis of rho minus sigma is not equal to the eigenbasis of rho and sigma?
Oh.
Or just this is an assumption for generality? No, okay.
So this is just true in general. If rho and sigma commute, then they have the same eigenbasis, and then they're different. Their difference also has the same eigenbasis, but in general, that won't be true. Okay. Okay. Awesome. So for rho and sigma individually, all of these lambda i's will be positive. But for rho minus sigma, some of them will be positive and some of them will be negative. Okay. It turns out that the maximization ends up giving P equals sum over I such that lambda I is greater than 0. Just project onto those eigenvalues. Okay, so you want to apply a projector to this matrix, and you want that matrix to have as big trace as possible. The negative eigenvalues contribute negatively to the trace. The positive eigenvalues contribute positively. You just want to kill off all the negative eigenvalues. Okay, so you just left with the positive ones. You make it as big as possible. There's a bit of work to do because the projector could work in some different basis. The eigenbasis of rho minus sigma. You want to show that I can't do better, but it turns out this is indeed the case. Okay. So what does that mean? It means D rho sigma equals just the trace of P rho minus sigma. Oops. But that's just equal to the sum over the positive eigenvalues of rho minus sigma. Okay. Note that the trace of rho minus sigma is equal to the trace of rho minus the trace of sigma, which is equal to 0. So that means the sum over the lambda i's that are greater than or equal to 0 is equal to the sum over the lambda i's that are less than or equal to 0. Okay. So the sum over the positive eigenvalues is then equal to a half the sum over all eigenvalues of modulus of lambda I. Sorry. Okay. Just because the negative ones and the positive ones have up to the same thing. So if we just add up all the absolute values, we'll get twice that. And in turn, this is equal to a half the trace of, it's called the modulus of rho minus sigma, which is basically equal to, it's called the matrix square root of rho minus sigma squared, but it really just means literally the thing written above of you just take all the eigenvalues of rho minus sigma and you take their absolute value. Okay. This trace of the modulus of rho minus sigma has a name that you'll also see. It's written like this. It's called the matrix 1 norm of rho minus sigma. Okay, but don't worry too much about that. The key point is that this distance between rho and sigma, defined by this operational definition in terms of how well you can distinguish them with a measurement, just ends up telling you, ends up being the sum over the positive eigenvalues of rho minus sigma. Okay, so let's briefly discuss some nice properties that has this trace distance has as a measure of how distinguishable states are. First, it obeys what's called the triangle inequality. What does this mean? It means that the distance between rho and tau is less than or equal to the distance between rho and sigma plus the distance between sigma and tau. Okay, and the proof of this is very simple. Distance between rho and tau is by definition equal to the trace of some projector times rho minus tau. But that is equal to the trace of the same projector times rho minus sigma plus the trace of that projector times sigma minus tau. Okay, just because the trace is linear. And then by definition, the dist d of rho sigma is defined as the maximum of trace of p times the rho minus sigma, where we maximize over all p's, but this is some particular p that maximized the trace of p times rho minus tau. So this trace is smaller than the distance between rho and sigma, and the second trace is smaller than the distance between sigma and tau. Okay, and that's exactly what we wanted to show. So this is, if we have a triangle where at different points in the triangle, the density matrices rho, sigma, and tau, then the length of this side in the metric given by this trace distance plus the length of this side is greater than or equal to the length of just going directly between the two. Okay, so triangle, that's a pretty sensible property for a triangle have if you want to meaningfully call something distance. So yeah. Okay, and the second definition, something called monotonicity. So if we have two density matrices, rho AB, sigma AB, okay, then the distance between them is greater than or equal to the distance between the reduced density matrices, rho A and sigma A. Okay, so by losing access to system B, then rho and sigma become harder to distinguish. Again, this is very simple to prove. D rho A sigma A is equal to the trace of some projector on A times rho A minus sigma A, which in turn just equal to the trace projector on A times the identity on B times rho AB minus sigma AB. But this projector tensor, the identity matrix, is just a projector on AB. And so this is less than or equal to the distance between rho AB and sigma AB. Okay.
I'm sorry, I think I just missed this. What do these indices represent?
Yeah, we're just imagining, have some Hilbert space H, HA tensor HB. Okay. And we're comparing rho AB is the full global density matrix on the full Hilbert space. And then just rho A and sigma A are the reduced density matrices just on A. Okay.
Thanks.
So the point is, if we just look at the state on A, then we can distinguish rho and sigma less well than if we're allowed to look at the whole state on A and B. Okay, it's a very intuitive property.
Sorry, how did you get the inequality there again?
Sorry?
How did you get the inequality again?
Yeah, because this is a projector on AB. But this is by definition the max of the same formula over all projectors on AB, right? So this is some projector, this is the max over all projectors, and so the first has to be smaller than the second. Okay.
Yeah.
Awesome. Okay, so our second definition is going to be the fidelity. And that starts from the following observation. So that if we have any density matrix rho, can be written as sum over I, pi, psi I, then we can find some pure state psi on A and R. R here is sometimes called a reference system. It's just an extra Hilbert space we've just added in for mathematical reasons, such that rho A is just the trace over R of the pure state psi. Okay, so for example, psi could be equal to sum over I square root pi psi I, right, where this is psi I on A and psi I on R, and we just assume that R is isomorphic to A. You can check very easily that if you do a partial trace of this, you know, this is just the Schmidt decomposition that we talked about a couple of lectures ago. We do a partial trace, we just get back that density matrix. Okay, so this state psi AR is called a purification of rho. Okay. Turns out, in fact, that any two purifications psi and psi prime can be related by psi prime being equal to some unitary acting only on R times psi. Okay, that's just a fact that yeah, you guys can check for yourselves and satisfy it.
Really quick question. Does
Yep.
the example purification you gave, does this rely on the psi i's being orthogonal, or is this work if they're
Yeah,
not?
the psi i's are orthogonal because it's the eigenbasis of rho A.
Oh,
Good
sure.
question.
Okay.
Yeah. Yeah, very good question. If the psi i's weren't orthogonal, then that would not be true. Yeah, I'll put that there. Yeah, it really, if this was just some arbitrary ensemble and not the eigenbasis of rho, that would not work at all. So it's good to point out. So what we're going to do, we're going to define the fidelity of rho and sigma based on the inner product of purifications of rho and sigma. right? So from these states, rho and sigma, we can naturally construct pure states that are purifications of them on A plus this additional reference system. And then we can use those purifications to define the fidelity. And in fact, the way we define the fidelity, this is the max over all possible purifications of rho and sigma of modular squared psi rho and psi sigma. Okay, so it's always possible if you have a large enough reference system to find two purifications that would be orthogonal, just because you can just tensor in an extra 0 state for one of them and an extra 1 state for the other, and that will make them orthogonal. But this maximum in a product is sort of well defined. It's non-trivial. It's not always equal to 1. If rho is not equal to 0, it actually can't be equal to 1. And this is it's a nice measure of how different rho and sigma are. That in some ways is worse than trace distance, and in some ways is better. Okay. Turns out, I'm not going to go into the details of the proof of this. You can look it up in Nielsen and Schwang or anywhere you like. This is actually also equal to a matrix 1 norm, just like the trace distance was. And in this case, it's actually the square of the 1 norm of rho to the half sigma half. Okay, again, yeah, this is called Ullmann's theorem. I'm going to skip the proof because it's not super enlightening. You guys can look it up if you care. But the key point is that you can compute this thing without having to go out yourself and maximize over all possible purifications. It has a nice, simple, explicit formula that you can prove it gives the same answer. So some properties of the fidelity, which I think I might put on homework sets, so I'm not going to prove them again. The first one, it's quite nice that it has the trace distance doesn't actually. It's what's called multiplicativity. Yeah, so I should say, by the way, unlike the trace distance, where it's like if the states are the same, then trace distance is equal to 0. And if they're maximally distinguishable, trace distance is equal to 1. In this case, if they're the same, then the fidelity is equal to 1. And if it's equal to 0, then it implies that rho and sigma are orthogonal. I should have said this about the trace distance too. Let's just write it up here. Note d rho sigma equals 0 implies rho equals sigma. D rho sigma equals 1 implies the two density matrices are orthogonal.
What do
Okay.
you mean by the density matrices?
Yeah, it's a good question. It means that, so rho and sigma have some support, right? They have some subspace that they don't annihilate. It means that those subspaces are orthogonal. So another definition would be the trace of rho sigma is equal to 0. Okay, so properties of the fidelity. The nice one it has the trace distance doesn't have an equivalent of is that if I have two product density matrices, so rho A tensor rho B, and sigma A tensor sigma B, then their fidelity is equal to the product of the fidelities of rho A and sigma A and the fidelities of rho B and sigma B. And the second property is, again, we have a monotonicity. In this case, the fidelity being smaller roughly corresponds to the states being further apart, being more distinguishable, more different at any rate. And so in this case, it's the fidelity between rho AB and sigma AB is less than or equal to the fidelity between rho A and sigma A. Fidelity can only increase when you do a partial trace over one of your subsystems. Okay. So that is basically all I'm going to say on these things. I really want to just briefly introduce them because they're things that will show up as like measures on density matrices all the time if you do other stuff in quantum information. Final comment I'm going to make is, okay, this is a bit unsatisfying, the fact that there are these two different measures, right? Like the pure states, we just have a canonical notion of how different they are, which is just the inner product. But here there's sort of these two different ones that seem kind of different. And the answer is that, well, they both have their advantages and disadvantages. Particularly, often it's easier to prove things about one than it is about the other, and vice versa. But often, which you use doesn't matter too much. And that's because they're actually related by what's called the Fuchs-Van de Graaff inequalities. Which say that 1 minus the square root of the fidelity is less than or equal to the trace distance, but the trace distance in turn is less than or equal to the square root of 1 minus the fidelity. What this means is if the trace distance between rho and sigma is very small, then that implies the fidelity between rho sigma is very large, very close to 1. And also the other direction, that the approximations get worse a bit each time you go across from one to another because these inequalities aren't strict. But if the trace distance is sort of equal to epsilon, then the fidelity has to be less than 1 minus square root epsilon and vice versa. And similarly, so that's if states are roughly the same. Similarly, if the trace distance between them is roughly 1, so they're like almost orthogonal, then the fidelity between them would be roughly equal to 0. Okay. So if you don't care too much about the exact details of how close they are to 1 and 0, and you just care that they're very close in some limit, then it doesn't really matter if you use trace distance or fidelity. Okay. Okay, so that's all I'm going to say about those two things. And I'm going to move on to, I think it's probably the more interesting and important part of today's lecture, which is going to be on quantum channels.
Could I ask a quick question?
Yes, absolutely. Yeah, any questions on fidelity or trace distance? Now's the time to ask. So go ahead.
So we can view these density matrices as just matrices themselves. Could we use like normal matrix norms, like the Frobenius norm? And
yeah. So yep. So the trace distance basically is, up to a factor of a half. It is the matrix 1 norm. It turns out that this is the sort of physical, like all the other matrix norms. You've got like the Hilbert-Schmidt norm. Got the Frobenius norm, you've got the operator norm. It turns out for density matrices, they're not physically significant. So it's the one norm that controls, has this actual physical interpretation of how distinguishable, how easily they can be distinguished by a measurement. And so that's the, it's the thing, for example, that for pure states ends up corresponding to being equivalent to the inner product. It's related to the inner product by a simple formula. Whereas for the other matrix norms, that just won't be true. So yeah, these are the, you could define a lot of other norms. They can be useful in some circumstances, but they're not physically significant in the sense that, like these properties of being close to density, trace distance close to 0 and fidelity close to 1, trace distance close to 1 and fidelity close to 0, they're the right definition of almost the same state and almost orthogonal states. And if you used other norms, particularly if your Hilbert space is big, then the definitions you get from them would not be equivalent and they'd just be wrong. It's like for the pure states, the right notion of distinguishability is the inner product squared, which is like a 2 norm. You could also define like a 1 norm, L1 distance between states and stuff, but that wouldn't have any physical significance. Okay.
Thanks.
Any other questions?
I have one question.
Yep.
When I guess when Google talks about how their qubits have like some 90-something% fidelity, are they using this definition?
Yeah, it's the same definition of fidelity. They're often talking about the fidelities of their gates. So that's like a slightly more general definition. It's the fidelity of what happens when you apply an operator to a gate, but basically the same thing. Basically, it's about the fidelity of between the state you would theoretically get and the density matrix that you would like actually get in practice. But yeah, it's the same, certainly the same fidelity.
How do you
now you know what that means?
Okay. How do you usually like pick this reference system? It seems kind of
yeah, it's the answer is it doesn't really matter as long as it's big enough. The dimension of the reference system needs to be at least as big as the dimension of your original Hilbert space. But as long as it's that big or bigger, it doesn't matter for the definition. That's a very good question. I didn't want to get too much into details of that, but yeah.
Just like, what would be like an example of a reference system?
I mean, it's just a mathematical object, right? It's not a physical thing. So the most common thing to do is you just treat it as another copy of the same Hilbert space as your original system. But it's really just a purely mathematical construction. There's no, you don't actually build a physical reference system. You just like, yeah. I guess what the reference system really is the rest of the universe, right? If we assume the state of the universe is pure, then if the system's in some mixed state, that state must be purified by the rest of the universe somehow, and you could call that your reference system. But when we're doing the calculations, we normally just treat it as another copy of our original system.
Okay, cool. Thank you.
Cool.
Can I ask a question about the reference system as well? So like, could you have like 2 separate reference systems that are like entangled with each other in some sense? Like it seems like kind of arbitrary, like even though they're not physical, like could you apply like physical
you
principles to
could,
them?
but yeah, you could have the reference system be a tensor product of reference system 1 and reference system 2. But then when we look at the definition of fidelity, for example, we wouldn't be distinguishing like that tensor product factorization wouldn't matter at all, right? We'd still just be treating it as one big Hilbert space. And so it would work exactly the same way. Yeah, again, good question. Okay, awesome. Any other questions? Otherwise, we'll go on to quantum channels. Okay, so let's say I have some density matrix. Right, okay. We want to answer the question of like, what can I do with my density matrix? So if I had a pure state and we were just evolving it to another pure state, then the only way it could evolve would just be via a unitary matrix, right? But now we have density matrix, we can do sort of more. The first thing that we can do is that we could imagine adding in some extra system. Just in a fixed state psi. Right, we don't want to, we want our only input to this thing to be the density matrix. So we don't want to allow like, you know, the state of this extra subsystem to depend on the input in any way. But we could imagine just we add in some extra fixed state so that our original density matrix, rho A, goes to rho A tensor psi psi. Okay, and again, I'm going to call that system R. Okay, what's the second thing we can do? Well, we can do some unitary evolution, right? But there's no reason that unitary evolution just has to act on A. It can also interact A with this extra system that we added in state R. Right, so we have some unitary that acts on system A and system R. That evolves our state. And then finally, we could imagine throwing away some subsystem. Okay, so for example, we could say, okay, but at the end of the day, we don't care about the state of subsystem R, we just care about A and throw that away. But in general, you know, we don't have to throw away the same subsystem R that we threw away initially. We can just say that our Hilbert space, which we thought of as you know, H, that we thought of previously as a tensor product of H, A, and R, is actually also equal to a tensor product of some HB and some HE. These are just conventional letters, so I'm going to use them. And then we can say that we're going to do a partial trace. We're going to throw away subsystem E. E is called E because it represents the environment that we lose access to. Then we have our final density matrix on subsystem B. It's given by a trace over E of this unitary acting on rho A tensored in with this fixed state psi. Okay, and we call this rho B curly N acting on rho A. Okay, so curly N is a map from a density matrix, so an operator on HA to an operator on HB. This is called a super operator. It's a map between operators, which themselves are, of course, maps between states. And we call this whole thing, this is basically the definition of a quantum channel. Turns out this combination of three things, adding some extra stuff, interacting everything together, throwing away some stuff, is sort of the most general thing you can do to your initial density matrix to end up with some final density matrix. Okay. So this is sort of kind of complicated having it in 3 steps. Steps 1 and 2 can actually be nicely combined together. Into a single linear map that I'm going to call V, that takes HA into HB tensor HE. This lets us stop talking about R entirely. Okay, and the only property, extra property we need to require is that V dagger B is equal to the identity on A. Okay, this ensures that V can be thought of as adding in some extra fixed state psi and then applying a unitary operator. Okay, so this map V is called an isometry. It's roughly speaking the analog of a unitary where the sort of starting system is different from the final system. Okay, so it's a unitary from HA to the image of HA, and HB tends to HE, but that's just some subspace of HB tends to HE. So in particular, V dagger is not equal to the identity on B tensor, the identity on E, because that's just impossible, right? The dimension of A is going to be smaller than the dimension of HB tensor HE. Okay, so then our channel is just defined. N of row A is equal to a trace over this environment system E of V row A V dagger for some or some isometry V. Okay, and that is going to be definition 1 of a quantum channel, sometimes called the Steinspring representation of the channel. Okay, any questions on that part?
What do you mean when you say like HA cross HR is nearly equal to HB cross HE?
Oh, but by nearly let me just write this as equal. I just meant that they're isomorphic, that they're the same Hilbert space. That does not mean approximate. It means that they're isomorphic. So it means they're the same Hilbert space, right? Imagine we had, we have some, say, 12-dimensional Hilbert space. We can think of that as a tensor product of, say, a 4-dimensional Hilbert space and a 3-dimensional Hilbert space, or we could think of it as a tensor product of a 2-dimensional Hilbert space and a 6-dimensional Hilbert space. There's different ways to think of it as a tensor product, and we're just saying that these are two different ways.
So like you start out with like a 3x4, and then you end up 2x6. Then when you say throw away some subsystem, you can like
you're throwing away the 2, say.
Okay.
Cool. Yeah, great questions. Really keep the questions coming. I really appreciate them because it's really useful for me to get feedback when it's on Zoom like this.
Can I ask a question as well?
Yep.
So with that relationship where you're talking about like a reference system and then like some other type of Hilbert space and how it's like nearly equivalent to like the environment.
It's not nearly equivalent. It is actually equivalent. There's no.
So because they're isometric. Yeah. Okay.
Yeah.
So does that say anything about like your reference system in relation to like an environment? Like is there any type of like physicality?
Yeah, I mean the reference system here I called it R, but here it is actually physical, right? Because it's we have some subsystem A of like a big Hilbert space that includes our environment as well. Then we add in the environment, interact it with the environment, and then throw away an environment. But exactly what counts as the environment at the end is not necessarily the same as what counts at the beginning. Let me instead call this E prime. Right, so this is the extra environment, the stuff that's not in A, right? We add the stuff that's not in A. And then if B was the same as A, we would just be throwing away the same environment. E prime would be the same thing as E. Okay, but instead we're going to allow this to be more general. We're going to be allow say like maybe A consists of 100 qubits, but at the end of the day, we only keep 10 of them, right? Then there's extra stuff in E that wasn't initially in E prime. That's all this means. Okay. Awesome. Okay. So this definition's all well and good, and it's in some ways the most physical definition, but we'd like a definition of a channel that doesn't involve sort of any Hilbert spaces other than like HA and HB, right? We have a starting Hilbert space HA that our initial state is a density matrix on, and we have a final Hilbert space HB that our final density matrix is going to be on, and we just want to talk directly about those two things. Okay. So how can we do that? Well, we can just choose some basis, ket I, for HE. Then we have V of psi can be expanded in that basis as Ki acting on psi times I. So I is E. Ki is again a Krauss operator, just like in the last lecture. But now it's a Krauss operator that maps HA to HB. Okay, so psi is in A, but Ki acting on psi is going to be in HB. Okay, and then the fact that V dagger V equals the identity is equivalent as before to the sum over I, Ki dagger Ki being equal to the identity. And we can now just do the partial trace over E very explicitly, right? So this is the partial trace over E of V rho re dagger. But V is the sum over I multiplied by ket I and tensor in I. So this is just a sum over I and J. Ki rho Kj dagger tensor ket I bra J. Right, so that's just applying V and V dagger to the state rho. But now this partial trace, these I's are just some orthonormal basis. Kills the off diagonal terms. And we're just left with N of rho being a sum over I, Ki rho, Ki dagger. Okay, so this is going to be our definition 2 of a channel. It's just going to have some set of Ki's mapping HA to HB such that the sum over I of Ki dagger Ki is equal to the identity, where the channel, and so the channel then maps rho to sum over I, Ki rho, Ki dagger. Okay, and this is called the Krauss representation of the channel. Okay, so that's all kind of abstract. Anyone have any questions on the Krauss representation and how we got to that from the Steinspring representation? You can also go the other direction, by the way. If you have a Krauss representation, you can just add in an environment and then define V as this sum over Ki psi Ki, and that gives you a Steinspring representation. Anyone have any questions on the Krauss representation? Otherwise, I'm going to go on to giving some examples of simple quantum channels.
In your definition for N in like number 3, you had like that unitary U. So in this case, is V the U? Is V acting as
here and yes. So V here includes both the add in an extra state on HE prime, right? To make it not just a map on HA, but a map from HA to HB tensor HE, and then apply some unitary after you've done that. Right, so it combines those two things together into a single operator, and the only condition that single operator needs to happen is it needs to be linear from HA to HB tensor HE, and it needs to have V dagger V be the identity, because this needs to be a fixed state, and this needs to be a unitary. Okay.
Okay, yeah.
Awesome. Okay, so let's do some simple examples. And we make all of my examples be just channels mapping a single qubit to the same single qubit, okay? Just because if you start getting bigger Hilbert spaces, then it starts getting pretty complicated and confusing pretty quickly. Okay, so example 1 is going to be what's called the dephasing channel. Okay, and in this case, we're going to have two Krauss operators. The first is going to be square root 1 minus p times the identity. And, wait, is that right? Yeah, I need to divide by square root 2 here. Yeah. And the second is equal to square root p over 2 times the Pauli matrix Z. Okay, so we can check K0 dagger, K0 plus K1 dagger, K1 is equal to 1 minus P over 2. Sorry, I shouldn't have had that one. Oops. Don't know why I added that factor of square root 2 in there. So K0 dagger K0 is equal to 1 minus P times the identity. K1 dagger K1, Z squared is the identity, so that's P times the identity. And so this whole thing is equal to the identity. Okay. So now we can look at what this does to a density matrix rho. Say rho equals A, B, C, D. Okay. So rho goes to 1 minus P times the identity times rho times the identity dagger, that's just rho, plus P times Z rho Z dagger, which is just Z. Okay. I know what I screwed up here. Yeah, we want to make this P over 2, and we want to make this P over 2. Sorry about that. Change my definition of P. I knew there was a factor of 2 that should be in there somewhere. Okay, so what does this do to our actual explicit 2 by 2 density matrix? Well, we have 1 minus P times just the same thing, plus P times what's Z rho Z? Well, it gives a phase of -1 to everything that's in the bottom row, and a phase of -1 that's everything that's in the second column. So that ends up being just flips the sign of B and it flips the sign of C. So this ends up taking A just goes to 1 minus P over 2A plus P over 2A. So it just goes to A. B just goes to B. Sorry. D just goes to D. But B goes to 1 minus P over 2 times B, staying the same. But there's a P over 2 probability that B goes to minus P, right? Because we've done this phase flip. And so eventually we get 1 minus P times B and 1 minus P times C. Okay, so what this channel is doing is it's like damping down the off diagonal terms in the density matrix. In particular, if we set P equal 1, the sort of totally dephasing channel, then this just becomes equal to A0, 0D. Okay, can anyone tell me what that channel corresponds to as a physical operation?
Measurement in the Z basis.
Indeed. So what does this do? If we had some state that was like psi, where psi is alpha 0 plus beta 1, right? Then that is equal to modulus of alpha squared 0, 0 plus beta alpha star 1, 0 plus alpha beta star 0, 1 plus modulus of beta squared 1, 1. Okay, and so then that goes to just modulus of alpha squared 0, 0 plus modulus of beta squared 1, 1. This is if p equals 1. Okay, and that is just a classical mixture of being in the state 0 and being in state 1. Okay, so this has got measured in the computational basis. So in general, dephasing channel corresponds to sort of a partial, some probability p of a measurement happening in the computational basis. Okay. Example 2, it's going to be called the depolarizing channel. This time we're going to have K0 is equal to 1 minus 3p over 4 times the identity. K1 is going to be square root p over 4 times the X matrix. K2 is going to be square root p over 4 times the Y matrix. K3 is going to be square root p over 4 times the Z matrix. Okay. What does this do to an input state? Well, rho goes to, goes to 1 minus 3p over 4 times the identity plus, 1 minus p3 over 4 times rho, I apologize. Identity, rho, identity, which is just rho, plus p over 4 times x, rho, x, plus p over 4 times y, rho, y, plus p over 4 times z, rho, z. You can check that 1/4 times rho plus x rho x plus y rho y plus z rho z is actually equal to 1/2 times the identity. It's actually independent of rho. So what this actually takes to rho 2 is 1 minus p times rho plus p over 2 times the identity. Okay, so what's this doing? It's roughly just randomizing the state. On the Bloch sphere, it's leaving theta and phi the same because the eigenvalues of 1 minus p times rho plus p over p times half the identity are exactly the same. But it's mapping r to 1 minus p times r. So it's moving everything towards the center of the Bloch sphere. It's doing some noisy thing. And if p equals 1, then it's just mapping everything to just maximally mixed state. So it's just completely, everything's getting swamped with random noise. There's no record of what the original state was at all. Okay, so this is an important point about channels. Unlike unitary evolution, channels are not generally reversible. So there's generally not some inverse channel that can take you back from your initial state to your final state. For example, depolarizing channel with P equal to 1, then everything gets mapped to the maximally mixed state. So clearly there can't be anything that gets you back your original state because it's just been totally forgotten. But actually, even for the depolarizing channel with any non-zero P, then there's no channel that gets you back to the original state because the sort of the linear map that would do so cannot be written in a Krauss decomposition. Okay, so that pretty naturally brings us to the task of listing some nice properties of quantum channels. We've had a lot of listing properties today. It's been a lot of like just defining things and maths and so on. Sorry about that. We'll get into cool physics soon enough again. So the first property is, of course, that a channel is linear. Okay, you can just check using either the Krauss or the Steinsprung definitions that n of rho plus sigma is equal to n of rho plus n of sigma. This is pretty manifestly true. Second property is that it's trace preserving. So what does this mean? It means trace of n of rho is equal to trace of rho. Okay, so this is just, yeah, let's just do this explicitly. This trace of sum over I, ki dagger, sorry, ki rho, ki dagger, which is equal to trace sum over I, ki dagger, ki times rho, which is equal to trace of rho. Okay, so this is obviously good. It means that if we start with some density matrix, trace 1, then it stays trace 1. And the final thing is that it's positive, which means if rho is a positive semi-definite operator, then any state psi, n of rho psi is equal to a sum over I psi ki rho ki dagger psi. But each of these terms is greater than or equal to 0 because rho is positive, semi-definite. So by definition, each term is greater than or equal to 0. That means the whole thing is greater than or equal to 0. Since this is true for any state psi, then n of rho is positive semi-definite. So rho, the channel n takes positive semi-definite operators to positive semi-definite operators. Okay, a density matrix is a trace 1 positive semi-definite operator. So 2 plus 3 basically means channels map density matrices to density matrices, which is good because we sort of constructed them to do that. So not super surprising. Okay. So a very natural question you might ask is a linear trace preserving positive superoperator always a channel? Anyone want to guess an answer for this? So the answer is in fact no. Might hope it was true, but it isn't. You can give a simple counterexample that is a linear trace preserving positive superoperator, but is not a channel. And then it doesn't have a Steinspring or a Krauss representation. It's also not something you can physically implement. And that's just what's called the transpose map. Just takes rho to the transpose of rho. Okay. So why is this? How do we know this is not a channel? Well, let's imagine we have a state of 2 qubits. And we're going to apply transpose to qubit A, but not B. Okay, so if we had some channel and then we tensored it with having some extra Hilbert space that we just did nothing to, we applied the identity to, that would definitely still be a channel. You can check this very easily using the Krauss or Steinspring representations. But if we take the transpose and we tensor it with the identity, and then we apply it to the Bell state, phi plus. So this is equal to a half 0, 0 plus 1, 1 tends to 0, 0 plus 1, 1, or expanding it out, 0, 0, 0, 0 plus 0, 0, 1, 1 plus 1, 1, 0, 0 plus 1, 1, 1, 1. This will go to, okay, so we have 0, 0, 0, 0. We transpose the first qubit, so the 0 gets switched with the 0, but that's still just 0, 0, 0, 0. What about the second term? Now the 1 in the ket bra of the first qubit gets switched with the 0 in the ket of the ket of the first qubit. So that goes to 1, 0, 0, 1. So we're transposing the first qubit, but not the second. 1, 1, 0, 0 goes to 0, 1, 1, 0. And finally, 1, 1, 1, 1 just stays the same. Okay. And now if we look at this whole matrix, then you can easily check that the state 0, 1 minus 1, 0 has eigenvalue is an eigenvector of the state, and it has eigenvalue minus a half. Okay, and so this whole thing is not a density matrix. So we know for sure that transpose tends to the identity can't be a channel, but that means the transpose itself is not a channel.
Could I ask a question?
Yep.
So based on like what we've shown with like what Krauss operators can actually do and talking about like transformations on the density matrix, it sounds like you almost could use them for talking about like errors that come up in the environment. Like
yes, definitely, and that is going to happen later on in the course.
Okay, cool.
That's a preview for 2 or 3 lectures time, maybe 4 lectures time, when we're going to get into quantum error correction, and we're going to use exactly this sort of formalism to talk about quantum errors. Yeah.
Awesome. So what's like the right way of viewing it then? Because it sounds like almost, even though you're using like unitary operators in the like formalism for like how you define the Krauss operators, it almost seems like they're unitary transformations like acting on the density matrix that kind of jumbles
the unitary operators acting on the density matrix together with information being lost to the environment. It's a combination of 2 things, right? There's this reversible processing happening of unitary stuff going on, and then there's potentially information being lost to the environment. And errors are sort of more, well, errors can be both. But yeah, the Krauss operators are sort of a combination of the 2 things. Like each Krauss operator can be thought of as the stuff being lost to the environment and being in one particular state, and then the sort of the Krauss operator itself also contains the unitary evolution that happens. depending on that measurement outcome. So it's they sort of combine together two things in a weird way. Okay, I'm going to go on and just, there's one last thing I want to cover, and it's almost the end of the lecture. So I'm just going to try and get that done. So for N to be a channel, we need N tensor the identity channel to also always map positive operators. It's just to map positive semi-definite operators to positive semi-definite operators, right? Because otherwise N tensor the identity clearly can't be a channel, and if N was a channel, then N tensor the identity should also be a channel. So this, if it does so, we say that it is completely positive. Okay, so just positive means just N maps positive operators, positive operators. Completely positive means that N tensor the identity always maps positive operators, positive operators. Turns out that any completely positive trace preserving linear superoperator is a channel. So this is going to be our definition 3 of a channel, is it's any linear superoperator that's completely positive and trace preserving. Okay, so I'm going to sketch a proof of this thing. I'm not going to be super careful proving it rigorously, but let's at least give you a sense of how it works. And the trick is, again, that we're going to use a reference system. We're going to define phi, maximally entangled state, phi, sum over j, ket j on A, ket j on some reference system, okay, where j is just some orthonormal basis for each of them. Okay, and now we're going to imagine applying the channel N tensor the identity to this maximally entangled state phi. Okay, because the channel is completely positive, then this output has to be a positive operator. So this can be written as a sum over j, pj, phi j, where phi j is some state in HB tensor HR. Okay. So we've used the fact here that it was completely positive. Otherwise, some of these eigenvalues could be negative.
Is this an assumption, or is this?
This is an assumption. So our theorem is that a completely positive trace preserving linear superoperator is a quantum channel in the sense that it has a Krauss representation and a Steinsprung representation. Okay, so we've assumed complete positivity, and that lets us get this fact. So we can then do the following. Can write square root of pi, sorry, square root of pj, phi j. I should have called this I. I'm going to call this I. as just by expanding it in canonical bases, J and K. I'm going to assume actually that the channel just maps A to itself here, just because I'm lazy. So we can, this is A, this is R, and this state is just always a superposition over those things. So we're going to call the matrix describing that superposition Ki JK. Okay. So this is just using the fact that the tensor product has a basis given by the products of the bases of A and R. But now we can write this as Ki acting on our original state, ket phi, okay, where Ki is just the matrix made out of Ki JK. So it follows that n tends to the identity acting on this particular state, phi is equal to sum over I, Ki phi Ki dagger. Oops, yeah. Now that's of course exactly what we wanted to end up happening. But at the moment, we've only proved it for this one particular state phi, right? And really, if we could have done this for sort of any arbitrary state, but it's not clear that the Ki's that show up for an arbitrary state will always be the same, right? But now what we can do is we can just say, let's choose some basis, psi j, which in turn can always be written sum over k, ujk, ket k. It's an orthonormal basis. For HA. Okay. Then you can check this state phi can be written the sum of j, psi j bar, where psi j bar is just a sum over k ujk star. Okay, you can just check that's true. It's just an exercise in how unitary matrices multiply together. What does this mean? It means by linearity of the map N and the fact that it only acts on HA, then for all J in this superposition, we must have that N takes psi j to sum over I, Ki psi j Ki dagger. Okay, so we've used the fact that we really used here the fact that this state is maximally entangled. That's why we needed the complete positivity to then say that for any state psi j, then this phi can be written as a superposition over psi j's, okay? And that tells us that for any state this must work, and then n of rho, sum over I, Ki rho, Ki dagger, as desired. Similarly, trace n of rho equals trace rho, applies pretty immediately, sum over I, Ki dagger Ki is equal to the identity. N is a channel. Okay, so that overran somewhat. Sorry about that, folks. But we're just before the Berkeley 10 minutes. So yeah, cool. See you all on Tuesday. Next time, we're going to introduce entropies. Awesome. Any questions, by the way? I know it's a bit late in time.
I had one. I guess I'm the. It's not really clicking for me. I'm just I'm trying to understand what space, if we're taking the tensor product of n with identity, n is acting on this density matrix of phi's. What is the identity acting on?
The identity, the phi is on HA and on phi is on HA and on HR, right? So the density matrix ket phi bra phi, psi is on maps on A, operators on A, tensor operators on R, right? The N is acting on the operators on A part. The identity is acting on the operators on R part.
Okay, all right.
Is that clear?
Yeah, that's clear.
Awesome. Yeah, this is honestly, when I first saw this proof, I got quite confused by, because like you've got, it's an operator on a tensor product, and then you're acting with it with a super operator that acts on half, but not the other half. I got really quite confused by it. You just need to spend some time like deconfusing yourself about what's going on and like really think about it hard. Or you can just accept the claim that any completely positive trace preserving linear superoperator is magically a quantum channel, decide this is not something you're going to worry about for the next while, and not worry about the proof. Because it does take a bit of time to get your head around this, like tensoring a channel with an identity and stuff. Yeah. Any other questions?
How is this completely positive something like the operator, super operator? How is this different from the transpose map cross?
Yeah, so the transpose map is positive in that if I just input a positive operator to it, then I always get a positive operator out, right? Because transposing preserves the eigenvalues. But when I tensor the transpose map with the identity, so when I have these two qubits and I transpose one of them, but not the other, and I started with a positive operator, namely the projectron of the Bell state, then I end up here with an operator that isn't positive, right? So that's why it's not completely positive, because the transpose tensor the identity is not a positive operator. It doesn't always take positive states, positive operators. That clear?
Tensor producting a positive super operator with the identity will not result in a completely positive operator.
No, not necessarily. Like completely positive means that when you tensor it with the identity, it will still be positive. It's like it's a condition on the original channel that says, even if you tensor me with the identity, I'll still be positive. Yeah, if it's just a positive operator, then that may not be true. When I tensor it with the identity, it can end up not being positive anymore. And that's what happens to this transpose channel.
And then, so I think you define like channels to be super operators, but
Yep.
It seems like a super operator should be acting from operators to operators, but like in like your examples of the depolarizing channel, it seems like the channel is acting on a state. So,
It's acting on density matrices, right? It's taking density matrices to density matrices, and density matrices are operators on the Hilbert space.
okay.
Right.
Yeah.
Yeah, the multi-layers is coming from the fact that the density matrices themselves are already operators, and then you want operators on density matrices, so those end up being super operators.
And then one more from last lecture. So
Yep.
you introduced measurements to be unitary, but then would that make measurements reversible in theory?
So they are, if you don't lose. Like, yes, if your measurement device and your system stay isolated, then even if the measurement has happened, then if you can end up controlling the Hamiltonian of that isolated system and no information escapes out of it, then you can undo the measurement. But if if a few photons escape off and like disappear off into space and you can't get them back, then it's no longer reversible. So in practice, it becomes irreversible whenever you lose control over it. Whenever you no longer have everything sufficiently isolated so that no information can just escape out into the environment.
Okay. I was under the impression that like measurements and observables, or actually observables are Hermitian. So I thought like that measurements would also.
So measurements done using the measurement postulate are irreversible. But as long as you're, as an observer, staying outside the system, and as long as you always keep it isolated, then you can think of the physical process of the measurement happening as just the measurement device becoming entangled with the system. And so then there's no irreversible stuff happening. It's all just unitary. Is that clear?
Okay.
Okay, awesome. Let me stop recording.